Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do see and appreciate the beauty in the simpler problems. So today we are back at it again. We continue from where we stopped in our last session. We had started looking at the qualifying exams for the MIT 2020 Integration B. We covered problem 1 to 20. Today we move forward to cover the last batch of problems 11 all the way to problem 20. So before I delve into our problems, I'd like to thank our subscribers. Thank you so much for the amazing support you continue to show us. We don't take that support for granted. It is your support that motivates us to come here time and again. For our first-time visitors here at Everyday Mathematics, we mainly go out there, we look at hard mathematical problems, we come back here with solutions, and we share them with you. For our repeating visitors who haven't subscribed to our channel, we do beseech you to subscribe to our channel because your support goes a long way in giving us the extra visibility that we do need. So these are our set of problems today. Problem 11, problem 12, problem 13, problem 14, problem 15, problem 16, problem 17, problem 18, problem 19, and problem 20. So we're going to just go one by one and try to solve them. So problem 11 is the integral from x equals to 1 over root 2 to x equals to 1 of the arcsine of x over x cubed. This is a very interesting problem. The first thing I would like to do is first of all substitute for arcsine of x, and that is by letting u be equal to arcsine of x, and thus sine of u equals to x, and therefore cosine u du dx equals to 1, and therefore we could substitute for dx with cosine u du. Now looking at the limits when x equals to 1 over root 2, that means that u is equals to arcsine of 1 root 2, and therefore u equals to pi over 4. When x equals to 1, that means that u equals to arcsine of 1, and therefore u equals to pi over 2. So substituting in the limits and for arcsine of x with u, we have the integral from u equals to pi over 4 to pi over 2 of u over sine cube u times cosine u du. I shouldn't be saying du. But so what we're left with here is, I beg your pardon, we're left with u over sine squared u cotangent of u. I should erase this. And that means that now we have our integral of u times the reciprocal of sine squared u is cosecant squared u times cotangent u. And so the derivative of cotangent of x is negative cosecant squared x, and therefore we can express this as u times the derivative of the negative of cotangent squared of u. Now we could take this as a product, and we're going to try to use integration by parts. Also notice we have created half here because when we differentiate cotangent squared, we'll have the constant of 2, and since we don't have that constant here, we have a constant that is supposed to have negated the two constants. So we have our half here to cater for this squared. Um, so what we can do now is we're going to integrate by parts. And so if we have a product of u and dv, and we consider dv as its derivative of negative cotangent squared of u, and this is our u. Therefore, the integral is going to be, first of all, the integral, the product of u and v with the appropriate limit minus the integral of v du. And since v is going to be negative cotangent squared u, and then our du equals to 1 since u is just this small, case u. So essentially we're left with the integration of cotangent squared u. And here, by applying the limits appropriately, when u equals to pi over 2, or when u tends to pi over 2, this u becomes pi over 2. Cotangent of pi over 2 tends to 0. So at the upper limit, this tends to 0. At the lower limit, since cotangent of pi over 4 is 1, we are left with just pi over 4 at the lower limit. So we're going to see that in detail. Also notice we have replaced cotangent squared u with cosecant squared minus 1. And that is from the identity sine squared x plus cosine squared x equals to 1 divided through by sine squared, and we get that. So as I said previously, substituting in the limits and obtaining the limit as especially at pi over 2 here, the integral of cosec squared is going to be negative cotangent u, and the integral of 1 here is going to be just u. And so substituting in the limits, as I said, this tends to 0. And this remains pi over 4. And with this at pi over 2, this tends to 0. And this is, in place of u, we have pi over 2 minus pi over 2 minus cotangent of pi over 4 minus pi over 4. So we are left with pi over 4 minus 0, 0 minus pi over 2 minus, in bracket, minus 1 minus pi over 4. So 1 comes from cotangent of pi over 4. And so simplifying that further, we have pi over 4 minus this pi over 2. Minus becomes plus pi over 4 plus 1. So plus pi over 4 plus pi over 4 is pi over 2 minus is pi over 2. This entire summation here tends to 0. And so we're left with 1 in bracket. And so our answer is 1 over 2. So problem 12 is the integral of the product of sine 2x and cosine x. And that is from x equals to 0 to pi over 2. So what you'd want to do is to express this sine 2x into the single angle formalism. So we have 2 sine x cosine x times the cosine of cosine x. And then looking at this component and also looking at sine x, the sine x is the same as the derivative of negative cosine x. And so looking at this part here, this means that also the product of this cosine x and the product of derivative of negative cosine x is the same as the derivative of negative of sine cosine x. Because if you do that, then you have first the cosine of cosine x times the product times the derivative of cosine x times this negative. So you get this product. Now, one other thing we could do now is we could now try to integrate by parts here, where we take this to be our capital U and this to be our dV, right? So if this is our dV, then in bracket is what we have our. So integration by parts, this means that now in brackets we have the product of U and V, so which is cosine x times the negative sine x cosine x, and the necessary limit, minus the product or the integration of the product of du and v. So du is negative sine x, and then dv, v is negative sine cosine x. So we have initially the negative sign was cancelled, and now we still have the negative sign from the derivative of cosine x. So now what we have here, this is a simple problem. Essentially, what happens is the integral in our hands is simply this here is the derivative of cosine x. And so applying in the limits, as we can see, at pi over 2 cosine of, since we have a negative sign, we can begin by substituting the lower bound first. So cosine 0, cosine 0, when we have cosine 0, this tends to 1, and this tends to 1. So we have 1 times sine of 1, and then this tends to 0, and this tends to 0. So this entire thing tends to 0, and so we have sine 1. And then now we have cosine x there with the limits as needed. We get cosine pi over 2, this tends to 0. And so we're left with cosine 0 here. And then cosine 0 is 1, so we have cosine 0, which is cosine 1. And so since this tends to 1, sine of 0 is 1. And we have negative here. This becomes plus cosine 1. So we have in brackets, we have first of all 2 times in bracket sine 1 plus cosine 1 minus 1. And this is the answer. Problem 13 is the integral from x equals to 0 to x equals to 2 pi of sine x minus x. So what we can do is we can, this is the sum of angles, or the difference of angles. So sine of a minus b is sine a cosine b minus sine b cosine a. So doing that, we have the integral of sine x cosine x minus sine x times cosine sine x. And as you can see here, this is very easy, because what this is essentially is the derivative of sine x, and this is plus the derivative of cosine sine x, taking into account this sign here. So essentially we just have sine x plus cosine sine x. Then we apply the limit. First of all, 2 pi. In this instance here, sine 2 pi is 0. Sine 0 is 0, so sine of 0 is 0. So this part goes off. But in this situation here, sine of 2 pi is 0. Sine of 0 is 0. So cosine of 0 is 1, and cosine of obviously 0 is. So this essentially, we're left with cosine 0 minus cosine 0, which is just leaves us with a trivial answer of 0 anyway. Problem 14, which is the integral of 1 over x minus 1 plus the summation from k equals to 0 to 2018 of k plus 1 times x to the power k over summation from k equals 0 to 2019 of x to the power k. So I would solve this. I would like to express this as I would like to expand this out. And that is the same as the integral of 1 over x minus 1 plus 1 plus 2x plus 3x squared plus so on up to 2019 times x to the power 2018 over 1 plus x squared plus x cubed all the way to x to the power. And as you can see here, this second part here of the problem is essentially the numerator here is the derivative of the denominator. The numerator here is the derivative of the denominator. So we have essentially natural logarithm of x minus 1 plus the natural logarithm of 1 plus x squared all the way to x to the power 19. Now, using rules of logarithm, this is the same as the product of x minus 1 times the product of the summation of x to the power k from k equals to 0 to k equals to 2019. And if you multiply that, it's the same as x times everything here minus 1 times everything here. So we are left with essentially just x to the power 2020 minus 1. Now I know in the online answers provided by the MIT integration team, integration B team, it is natural logarithm of 1 minus x to the power 20. This is the answer that I've obtained. If anyone out there has an explanation as to why they got their answer the way they did, please leave a comment on that. But this is the answer that I was able to obtain. Anyway, going to problem 15, which was the integral from x equals to 0 to pi over 2 of 1 over tangent to the power square root of 2020 of x plus 1. We can begin first of all by saying let x equals to pi over 2 minus u, and so dx equals to negative du. And when x equals to 0, that means that u equals to pi over 2. And then when x equals to pi over 2, that means that u is 0. So when we substitute everything here, we get an integral negative of pi over 2 to u equals to 0 of tangent of 1 over tangent of root of 2020 into bracket pi over 2 minus u plus 1. Now, this yet becomes cot. This becomes cotangent of u, right? The complementary function. And so we have the negative sign here. And so we can flip the limits to remove that negative sign. And so what we have here is that the previous integral of x from x equals to 0 to x equals to pi over 2 of 1 over tangent root of 2020 of x plus 1 is the same as the same integral with the tangent replaced with cotangent. So for example, if now we add, when we have 2I, adding the two integrals, first with the tangent and second with the cotangent, since we know these two integrals are the same, and then we expand the tangent and cotangent so that we have sine to the power root 20 and cosine to the power root 20. What happens here is that where now you multiply with cosine in the numerator and denominator, And here you multiply by sine, the numerator and denominator. And then you add the two integrals. You realize that the numerator and the denominator are the same, which obviously cancel. So we are left with the integration of constant 1. And so that means that x is what we get, and with the limits applied properly, we get 2I being equal to pi over 2. And so I, which is the initial integral, is pi over 4, since we divide both sides by 2. So this is our answer, which is interesting. Then problem 16, which is the integral of x times 1 minus x to the power 2020. The first thing you do is let u be equal to 1 minus x. That means that dx is equals negative du, or vice versa. And so applying in, substituting in the for u, so we have 1 minus u times u to the power 2020 as our integral, and multiplying through, we get u to the power 2021 minus u to the power 2020. Integrating that, we have 1 over 2022 times u to the power 2022 minus 1 over 2021 times u to the power 2021 plus the integration constant. Now substituting back for x, since x is, u is equals to 1 minus x, so we have 1 over 2022 times 1 minus x to the power 2022 minus 1 over 2021 times 1 minus x to the power 2021 plus integration constant c. Problem 17, which is the second to the power 4 times tangent of x over second to the power 4 plus 4. So essentially what we have here is that the numerator is a quarter times the derivative of sec squared x plus 4, and the denominator is sec squared x plus 4. Since the numerator of our integrand is the same as the derivative of the denominator, this now tells us that we have quarter times the natural logarithm of the function denominator, which is second to the power 4x plus 4, and then plus the integration constant. And that is our answer. Problem 18 is x to the power 2x times 2 log x plus 2. Now, as we know that any number, fx, and f, or any function is equal to the e times log, natural logarithm of that same function, fx. So we're going to apply this expression for x to the power 2x such that our integrand is that, and as we can see here, this here is the derivative of and after taking this out here, we can see that this here is the derivative of this expression. And that means that our integrand is e to the power 2x log x times the derivative of 2x log x, which is also the same as the derivative of e to the power 2x log x. That means that our answer is e to the power 2x log x plus integration constant, which takes us back to e x to the power 2x plus c, e being our answer. Problem 19, which is the integral from x equals to 0 to 1 of the square root of 1 minus x squared. Now, this is a very simple problem. So a quick thing is to substitute with the trigonometrical function, and sine is my trigonometrical function of choice. I would also use cosine theta, but let's use x equals to sine theta. Therefore, dx d theta is equals to cosine theta. And so dx can be substituted with cosine theta d theta. When x equals to 0, what that means is theta is 0. When x equals to 1, that means that theta is equals to pi over 2. Substituting appropriately, we get the integral from theta equals to 0 to pi over 2 of cosine squared theta. And then now expressing it in the double angle formalism, that means that we have the integral of cosine 2 theta plus 1 over 2. And that means that we have half, pulling this 2 out, of into brackets, half of sine 2 theta plus theta with the limits applied appropriately. As you can see, at the upper limit, 2 times pi over 2 is pi, so sine of pi is going to be 0. And also the lower limit, sine of 0 is 0. So this entire part goes to 0. But with the theta, we have pi over 2 minus 0, which leaves us with pi over 2 times a half. And so our answer is pi over 4. Problem 20, which is the integral of x to the power 5 times e to the power negative x to the power 4 from x equals to 0 to infinity. This is interesting. First, I would like to say, well, let u be equal to x squared, such that du dx is 2x, and therefore du over 2x is equals to dx. Now, when x equals to 0, that means that u equals to 0. When x equals to tends to infinity, u also tends to infinity. And so this integral now can become, I've decided to keep x here and avoid the cumbersome substitution for u, such because I knew this x and this x would disappear. And so we have half times the integral from u equals to 0 to infinity of u squared times e to the power negative u squared. Now this can also be expressed as the integral or the first of all half times half of the integral from u equals to 0 to infinity of u times the derivative of negative e to the power negative u squared. So we can use the integration by parts, taking this to be our dv, right? And this to be our u. So with this being our dv, our v simply is equal to negative e to the power negative u squared. And so integration by parts beginning with uv, so negative u times e to the power negative u squared plus, minus, first of all, the product of v and du. Since our v is negative, is e to the power u squared, to the power negative u squared, that negative and the minus multiply together, we have a plus here. And since du now becomes 1, so we have only the integral from u equals to 0 to infinity of e to the power negative u squared. Now with this, we look as u tends to infinity, this exponential part tends to 0, right? And when u is 0, this part also goes 0. So this entire part goes to 0, and we're left with a quarter times half. And since we are beginning from 0, but if we take the integration from negative infinity, because this is symmetrical about 0, about x equals to 0, so half of the whole integral from u equals to infinity to u tending to infinity to u tending to positive infinity. And as you can see, this is our Gaussian integral where the value is root of pi. And so our answer now is 1 over 8 times root of pi. And this is our final answer. So thank you so much for hanging around with us, solving these 10 problems. We've run through them quickly. If you have any questions or suggestions or points of correction, please leave us a comment. We'll be very glad to hear from you. If you've not subscribed, we encourage you to subscribe to our channel because your support would mean a lot. Thank you once again. Until next time, à tout à l'heure, à la prochaine fois.